Sensible and Insensible: How to Study the Unseen Universe. Welcome to this episode. Before we ask what the universe is made of, there is a more fundamental question. What, exactly, are we entitled to study? Some things stand directly before our senses. Other things do not. We can see a tree. We can touch water. We can feel heat. We can weigh iron. But we cannot place gravity in our hand. We cannot see momentum itself. We cannot touch time or distance. Yet we do not therefore conclude that these things are imaginary. This distinction between the sensible and the insensible is one of the oldest and most useful starting points for an inquiry into nature. Part 1. The sensible. Let us begin with what is immediately available. A stone is sensible. We can see it. We can touch it. We can weigh it. We can move it from one place to another. Water is sensible. Fire is sensible. A tree is sensible. These things present themselves directly to perception. Of course, even direct perception can deceive us. A distant object may appear smaller than it is. A stick partly immersed in water may appear bent. A moving object may appear stationary from one frame of reference. So sensible does not mean infallible. It means only that the phenomenon is directly accessible to our senses. This is important because direct experience gives inquiry its first material. We begin with what nature presents. We do not begin by inventing what we hope nature will contain. Part 2. The Insensible. Now consider gravity. We do not see gravity itself. We see a stone fall. We see planets remain in astronomical systems. We observe the trajectories of projectiles. From these phenomena we infer something that is not directly presented to our senses. Momentum is similar. We cannot see momentum as an independent object. But we can observe a moving body continuing its motion, or observe the exchange of motion in a collision. The unseen quantity is known through what it does. This is the central principle. The insensible is not necessarily unreal. It may be real, but inaccessible to direct sensation. Its reality is established through its consistent consequences. Part 3. How do we study what we cannot see? This requires discipline. The first step is observation. We collect phenomena faithfully. We do not alter the observation merely because it does not agree with our expectation. The second step is comparison. We ask whether the same relationship appears repeatedly. The third step is reasoning. If an effect is consistently observed, what cause or variable can account for it? The fourth step is testing. A proposed principle should survive examination in different circumstances. This gives us a path from the sensible to the insensible. Phenomenon. Observation. Comparison. Reasoning. And repeated testing. In this way, the unseen becomes scientifically accessible through its consequences. Part 4. The danger of confusion. But there is an important warning. Not everything that cannot be seen should automatically be called a real insensible thing. There is a difference between an unseen reality and an unverified idea. Suppose we observe a consistent phenomenon. We may propose an unseen variable to explain it. That variable becomes scientifically meaningful only to the extent that it connects with observations and makes reliable predictions. An imagined entity does not become real merely because it has been given a name. This distinction is essential. Science has always used concepts that cannot be directly perceived. But the scientific status of such concepts comes from their relationship with phenomena, measurements, mathematical consequences, and successful predictions. So we should not confuse unseen, unknown, hypothetical, and unreal. They are not synonyms. Part 5. Gravity as an example. Gravity gives us a useful example. We cannot directly touch gravitational influence. But falling bodies, planetary trajectories, tides, and many other phenomena provide evidence for gravitational interaction. Therefore, gravity belongs to the category of things that are not directly sensible, but are scientifically investigated through their effects. The same methodological principle applies more broadly. We should not ask only, "Can I see it?" We should also ask, "What does it do? Can its effects be observed? Are those effects repeatable? Can the proposed principle explain them consistently? Can it survive attempts to disprove it?" These questions transform an unseen concept into an object of scientific inquiry. Part 6. Theory and Reality. Here we reach an even more subtle distinction. A theory is not necessarily a thing. A mathematical description is not necessarily a physical object. A model is a representation constructed to organize observations and make predictions. This does not make theories unimportant. Quite the opposite. A successful theory can be one of the most powerful instruments of human understanding. But we should maintain the distinction between the phenomena of nature and the conceptual language we use to describe them. For example, curved spacetime is a theoretical description in general relativity. It is not something that we perceive directly with our senses. Its scientific significance comes from the fact that the theory makes predictions and provides explanations that can be compared with observations. So the careful question is not, "Can I see curved spacetime?" The better question is, what observable consequences does this theoretical description predict, and how well do those predictions agree with nature? This distinction protects us from both extremes: blind realism and careless speculation. Part 7. The unseen becomes accessible through effects. Think about the history of physics. Human beings first observed falling bodies. Then they began to measure them. They studied projectiles. They compared celestial and terrestrial motion. They discovered regularities. They constructed concepts. They developed equations. And gradually, phenomena that once seemed mysterious became subjects of precise scientific reasoning. The same pattern continues today. We cannot travel outside the universe and look at it from the outside. We cannot place the whole cosmos on a laboratory table. Much of cosmology therefore depends upon indirect evidence. Light arrives. Spectra arrive. Orbital motions arrive. Gravitational effects arrive. Radiation arrives. The universe reveals itself through consequences. The scientist's task is to follow those consequences carefully. Part 8. Why this matters for our study of locomotion. This distinction is especially important when we study motion. A moving body is sensible. Its trajectory can be observed. Its speed can be measured. Its acceleration can be calculated. But the variables we use to explain its motion may not themselves be directly sensible. Momentum is not a visible object. Impulse is an event or interaction whose effect can be measured. Gravity is not seen as an object, but its effects are measured. Therefore, when we study locomotion, we must keep three things separate: the body, the observable phenomenon, and the explanatory variable. Confusing these levels can lead to confusion about cause and effect. Part 9. The fivefold classification. The sensible and the insensible are therefore only the beginning. Once we recognize that not everything unseen has the same scientific status, we need a more refined classification. There may be things directly sensible. There may be things insensible, but strongly established through their effects. There may be theoretical constructs, whose physical interpretation remains under investigation. There may be hypotheses awaiting sufficient evidence. And there may be propositions that observation has ruled out. The exact classification must be developed carefully. Its purpose is not to create more terminology. Its purpose is to prevent different kinds of knowledge from being mixed together. That becomes particularly important when we study the universe. We need to know not only what we observe, but what kind of claim we are making about what we do not observe directly. Closing. The sensible gives us the beginning of knowledge. The insensible gives us depth. The senses tell us what happens. Reason asks why. Observation gives us phenomena. Inference takes us toward causes. Testing determines whether our proposed understanding survives contact with nature. And perhaps this is the most important lesson. The unseen should neither be worshipped nor dismissed. It should be investigated. If something cannot be seen, we ask what effects reveal it. If something is proposed but has no confirmed consequences, we call it a hypothesis. If a theory predicts phenomena successfully, we give it scientific weight. And if nature contradicts our idea, we must be willing to change the idea. That is the discipline of studying the unseen universe. We begin with what nature gives us. We reason toward what we cannot directly see. And finally, we return to nature and ask, does the universe agree? Thank you for listening. This is Sayad Mustanvali, author of The Universe and The Universe Univocally. In the next episode, we will go one step further and examine a broader classification of things, so that we can ask not only how to study nature, but what exactly belongs to nature and what belongs only to our descriptions of it.